All right, three types of bonds. The first one is an ionic bond when the metal becomes a cation, and the cation is going to be positive, and then the nonmetal becomes an anion, and the anion is negative. So the cation loses electron, the anion gains electrons. And so this is very common. Like we've talked about this a million times, right? It is the attraction between the two. The attraction between the two lowers the potential energy. And this is Coulomb's law. So Coulomb's law states, as the two come closer, the potential energy decreases. Let's write that out. Potential energy and the force of attraction increases. So as they get closer, sorry, just R. As they get closer, the potential energy decreases because they're getting closer, and so the numerator is getting larger relatively, and so the force of attraction is getting larger and the potential energy is decreasing. One is positive and one is negative. Okay? Covalent bonds, non-metal and non-metal are bonding, and they share electrons, and they share them equally and unequally depending upon electronegativity. Okay, now just a little aside, because we've been talking about this. Ionic bonds are type 1. Okay, type 1 naming. And just so that we remember it, an ionic bond for type 1 naming, you just name it. Because you have a metal and a nonmetal, you have the cation who keeps its name, and you have the anion who ends in IDE unless it's a polyatomic ion. You also have a type 2. In a type 2, you're going to use Roman numerals. For the cation charge, right? And then you're just going to name it. Then just name it. Again. So I would say, like, which lead is it? It's lead 4. And then I would just add on the anion, IDE, for the for a monoatomic anion or the polyatomic ion. But they are named exactly the same way, but because the transition metals have, except for those exceptions, the transition metals have multiple charges, you have to use the Roman numeral to tell your reader which one you're using. Then all you do is crisscross and your polyatomic ion or your monoatomic anion. Okay? All right, covalent bonds. These are type 3s. And for these, you're going to use Greek prefixes. And remember, no mono on the first element. Okay? That's it. So that's how you do it. So that's naming the ionic bonds, and that's naming the covalent bonds. Now, metallic, metallic bonds are transition metals, which have, because of the D and F, electrons, they have this sea of electrons, which is like practically the official name of it. It's a descriptive name, but it's practically the official name. The sea of electrons due to orbitals with bonding with nonmetals, right? The valence electrons are spread out across all of them because they're not tied down to their one atom. So because of that, this allows them to, it allows the metals to be malleable. Does anybody know what malleable means? Bendable, squishable. Yep. Malleable, which is bendable. Squishable. So it means this, like this, as well as this, bendable and squishable. It also allows them to be ductile. What does that mean? What does ductile mean? Able to be pulled into a wire like this. So that's a different kind of movement. And the reason that it is malleable or ductile is because the electrons roll like ball bearings. Do you guys know what ball bearings are? Okay. Like tiny little BBs that if you were to put your hand on top of those tiny little BBs, you would be able to go like this. Does that make sense? If you had BBs and you were able to roll, you could roll your hand around on top of the BBs like this, right? That's what ball bearings do. They make it so that you can like roll your hand around. So they allow the different electrons and nuclei to roll around freely around on top of each other, for easier movement. Okay? All right, next, Lewis dot structures. We're using valence electrons only, and we're always looking for that octet. So we're always looking for the octet rule, which is atoms will gain, lose, or share electrons in order to have a full octet, which is the s and p orbitals. So we have a foundational structure that we use that looks like this. We take the element's symbol. This is what I teach. A lot of teachers teach it differently. This is how I teach it. S, Px, Py, and Pz. This is just like the arrows. Remember we did the arrows with the electron structure, right? So if I were to do, for example, oxygen, 1s2, 2s2, 2p4. My arrows would go up, down, right? And then up, down, and then I have 4 electrons in my p orbitals, my p sublevel, the 3 orbitals in my p sublevel. So I would go 1, 2, 3, 4. Questions on any of that? So now I'm going to put them around my oxygen atom for my Lewis dot structure. I start with my S1 and my S2, and I don't really care about my 1s2. I only care about my valence electrons, and my valence electrons are 2s2 and 2p4. They are only the electrons in the outermost energy level. So I'm going to start with my 2s2, and then what I teach is, and you can do it however you want, but I teach it's exactly like my p orbitals. P1, P2, P3, P4. P1, P2, P3, P4. Okay? So if you look at calcium, you don't, to figure out how many valence electrons there are, just look at the periodic table. All you need are the S and P's. Okay, so you just look at the periodic table and count the number of S and P's for calcium. So my calcium would be basically would be argon, right? And then 4s2. So there's my 4s2, 2 electrons. My iron would be argon, and then 4s2, and then 3d6. So my valence electrons are 4s2 right here. That's all I care about. I don't care about the 3d6 because they are not in the outer energy level. Now, the reason Lewis dot structures are so important is because they can be used to show bonding, which even PhD students use them to show bonding. In fact, there is software that uses your keyboard just to have an arrow that goes like this. You know, a little arrow like this, and oh, that's a software button, you know, like Alt FX, and you get that, and Alt GX, and you get that. So there's like software that puts dots wherever you want it. It's really quite amazing because these PhD students have to type all these equations in, so they don't have to like arrow up to subscript and everything. They just have all the buttons, right? Okay, so let's see what this looks like. So we're going to show bonding. We're going to show the transfers of electrons. And the charge on the ions. Okay, so this is something that could show up on an exam. Use electron dot structures to show the bonding of potassium, for example, potassium and chloride. So here we go. So I have potassium, which is 4s1. There it is. And I have sodium, which is sodium chloride. Wow. Okay. And chlorine. That's much better. Here's 7. Okay, there we go, chlorine, right? Okay, so now what I'm going to do is I'm going to transfer that electron from potassium to chlorine. So I know that this is going to happen because chlorine has a higher ionization energy than potassium, because potassium wants to get rid of its electron because now it's full, and chlorine wants one because now it's full. So the next step in this is I have potassium, 1 plus, and I have chlorine, which now is full. We show this as a bracket with the ionic charge on the outside. That is how we show ions, as a bracket with the ionic charge outside when we're doing Lewis dot structures. A bracket with the charge on the outside. All right? And now what happens is this charge is attracted to this charge. So it's important to note that in ionic structures, it's not the transfer of electrons, it's the electrostatic transfer of electrostatic attraction of the ions themselves. This brings us to potassium chloride. Because the potassium positive and the negative are attracted to each other, not because of the transfer. We're going to talk about that in a minute, all right? So just a quickie here so that we can look and see what's actually happening here is potassium, which is argon 3s1, is transferring its electron to chlorine, which is neon, and then 3s2, 3p5. And so here comes that electron getting transferred over here, right? That's where it's going. So what we end up with in the end is, so that is what we end up with is potassium is now argon. Nope. Sorry. Nope. Sorry, I was trying to do that faster. Do not. So now potassium is 1s2, 2s2, 2p6. Because it lost that entire third energy level, right? Meanwhile, chlorine is now, so this is potassium plus, and chlorine minus is now 1s2, 2s2, 2p6, 3s2, 3p6. So now it has the same as argon. Everybody okay? So, yep. Sorry. Why did I not go up higher to begin with? That is the question. So this would be 3p6, 4s1. So this would then be 3s. No. 4s1, so it should have just been argon 4s1. 4s1. So then over here, this should have been neon to argon. No, the neon to argon. That's correct. This here should have been O to argon. Yes, I see what you're saying. 2, 3p6 to argon. Yes. Okay, so now the next one, the example is sodium and oxygen. So this is a little different. All right, so do this one now. Okay, remember you've got to get everything equal out, so you don't have to do the bottom part, the electron configuration. Just do the Lewis dot structures, okay? All right, so this is basically the same thing, except that each sodium is only giving up one electron. Oxygen needs 2. So the 1 electrons are going to fill those 2 spaces on oxygen, which, by the way, Hund's rule left those 2 spaces available for those 2 electrons to come in. That's going to give us 2 sodiums with a plus charge, a 1 plus charge. And the oxygens with a -2 charge, right? Then they're going to equal out, because +2 and -2, right? They're going to equal out, and you're going to get Na2O, which is how we get those subscripts. Those subscripts tell you that it takes 2 sodiums to balance out 1 oxygen. All right? Okay, moving on. All right, lattice energy. So lattice energy is the energy required to separate ions in an ionic bond. So when ions come together like sodium chloride, and that's the one we're going to use, they come together and they create this ionic structure that looks like this. It's not actually a bond like we usually think of as bonds. This is a cube. Can you tell it's a cube? Yes, we can, right? Doesn't it look like a cube? So I'm not going to draw lines connecting them. And here's why. But what I am going to do is I'm going to put like pluses and minuses, right? So this is going to be a minus, this is going to be a plus, this is going to be a plus, this is going to be a minus, this is going to be a minus, this is going to be a plus, right? So all of the pluses and minuses, so all of the positives are surrounded by minuses, by negatives, and all of the negatives are surrounded by positives. So they come together. I'm going to remind you that they join together into this tight lattice, like a fence, a lattice, right? A lattice structure is like this. This is like a lattice structure on a fence. You know, like a basket weave is kind of a lattice structure. They come together into this tight lattice structure, right? Lattice structure. And they come together into this structure because of the positives and the negatives attracting each other. Now remember back in solutions, I told you, we just talked about this, and I said it's really just a matter of a stronger positive charge washing by and pulling off the negative. Remember I told you that? And I said, so it's sort of like an ice cube that like the solutes are sitting there in a chunk, and then it's just a matter of the solvent dissolving off the top by being a stronger charge. Well, that's what this is about. How much energy will it take to pull this one off? So when a solute or whatever comes to wash this one and pull it off away from this lattice structure, how much energy will it take? All right, that's the lattice energy. So the way that this happens is it takes into account the fact that these are positive and negative charges, and where do they want to be? Next to each other. So it's sort of like positive and negative, they want to be next to each other, and so this is exothermic. So that means the energy required to separate them is endothermic. It's going to take energy to separate them. You're going to have to put energy in to pull them apart because they want to be together. Does that make sense? So how much energy does it take to pull them apart? Well, it depends on how much energy they actually released when they were put together, because they wanted to be together. So being together was good, and how much energy is it going to take to pull them apart? Well, how much did they want to be together? That's the way lattice energy. So things that don't really want to be together are going to come apart pretty easily. Things that really did want to be together are going to take a lot of energy to come apart. Okay? Now think about Coulomb's law. Charges, distance, size, right? Okay? That's how much they want to be together, and that's how much they want to come apart. Okay, now let's take a look. Ready? That's like the little introduction. Keep all that in mind, and here we go. All right, so here is an example. Remember delta H for formation, we are forming 1 mole of something, 1 mole. And so since we're only forming 1 mole, we're taking half of the chlorine, which was a diatomic element. So I'm only taking half of it, okay? So we're only forming 1 mole. This is the example that we're using, all right? So this reaction, ultimately, to form 1 mole of this is exothermic. So delta H formation of 1 mole of sodium chloride is exothermic. Sort of makes sense when you think about it. That makes sense because these guys are positive and negative. That makes sense. It seems like it should be exothermic. Okay. So let's look at the steps of this. How would this work? So first, the ionization energy for sodium, pulling off the electron from sodium, because we got to make it into an ion first because it's sitting there as a metal, isn't it? So we got to make it into an ion. So we're going to pull off the electron. That's positive 496. Wait, so we have to add energy in. Yes, we're going to add 496 kilojoules in to pull the electron off of sodium. Okay, that sounds good, right? And then we're going to add an electron onto chlorine to make it onto an ion, right? Right? We got to do that because we want those two, positive and negative, then they're going to attract, right? Okay, well, that makes sense too. And that's going to happen pretty easily because chlorine really wants that electron, right? So that's good. So that's going to happen pretty easily. That's exothermic. Problem is, you add those two together, it should be an endothermic process. That doesn't make any sense because a positive and a negative, they should come together pretty easily, and this should be an exothermic process. That would make sense. Doesn't make sense that sodium, which is positive, and chlorine, which is negative, coming together should take energy to put it together. But it's exothermic. So what happened in between there to make this an exothermic process, which it is? There must be more steps, right? Everybody understands where I'm going? There must be more than just pulling an electron off of sodium and adding an electron to chlorine and then sticking them together. Do you understand? So this is where this reaction called the Born-Haber cycle comes in, which is Hess's law. Hess's law said, if you can add up all the steps and they add up together, then you can add up all of the energies. In this case, it's the delta H formations. Now, how would they use this on a test? They would tell you it's very rare that it gets used on a test, but it's possible. But it would be, here are the steps, add them up, and find the missing step. You just need to know that all this, just like Hess's law, that's kind of a complicated process. We don't have a lot of time on a test. You just need to know they're going to add up together, and then you're going to subtract them to find the missing one. That's what you need to know for Hess's law. That's what you need to know for this, that all the steps have to add up together. So let's take a look at how this works, all right? So here is the original equation and the delta H formation, which if you look it up, the delta H formation is in that table, which hopefully I can scan it to you. Okay, so the first step is going to be the sublimation of the sodium because the sodium, the delta H formation is only for gas, only for gaseous elements. So the delta H formation is only for gaseous elements. So it has to be turned from a solid into a gas. That's the first thing that has to happen. So we're going to sublimate sodium. So when you do that, nope, you just didn't staple them in order. Okay. So when you do that, you're going to get, hang on, I gotta turn this. Right in here. Okay. When you do that, you get sodium, which is a solid, and you're going to sublimate it, which means it's going to go into a gas, right? And that is going to give you a delta H of step 1, and that's how we'll identify it as step 1. And that is going to be equal to positive because it's endothermic. We're going from endothermic, from a solid to a gas, right? So it's endothermic. 108 kilojoules. Step 2. Next, we're going to have to take Cl2 and we're going to have to separate it because we only want half of that. We only want 1 chlorine. So we're going to take 1/2 of Cl2, which is gas, and we're going to break that down into just chlorine, which is a gas. So basically, we're breaking it apart and just doing it. And that is called the bond energy, which, fascinatingly enough, the book just throws that in there, and it doesn't show up even as a definition for another 8 pages in the text. So the bond energy is the amount of energy that's holding the two together, kind of obviously, right? So we have to break that bond. So that's what has to happen. We have to input the amount of energy that's going to actually break that bond. So that's going to be delta H, and that's going to be step 2, which is positive 122 kilojoules. Next, step 3 is going to be, we're going to pull that electron off of the sodium. So now we're getting into more familiar stuff, right? We got to pull that electron off of sodium. So that's going to be sodium solid. Oh, sodium gas, sorry, we already sublimated it. And we're going to pull that electron off. So we're going to get sodium plus 1 gas plus that 1 electron, because there's that electron that we pulled off. So that's going to give us delta H3, and that is also going to be endothermic. There's a whole lot of endothermic going on here, right? And that's going to be plus 496 kilojoules. Now we're going to add that electron to chlorine, because we've got to electronegativity, right? We're going to add that to chlorine. So that is going to be, we're going to take that chlorine gas that we just had, we're going to add 1 electron, we're going to stick it on there. We're going to get Cl minus in a gas form, and that is going to be step 4, which is going to be equal to, and here's our first exothermic, 349 kilojoules. Now, step 5, this is where the big exothermic finishes, because what do these ions want to do most is they want to be like this. Woof. And they really do want that, and that is the lattice energy, right? That's the lattice energy. So we're going to get sodium plus in a gas plus chlorine in a gas, and that is going to make sodium chloride in a solid. And the problem is we don't know what this is. This is delta H5. And we don't know what this is. So the point is, what is this number, right? So what we're going to do is we're going to say that, okay. So what we're going to say is that delta H is equal to delta H1 plus delta H2 plus delta H3, and this is where Hess's law kind of comes into, plus delta H4 plus delta H5. So if we add all of these up, we should get the delta HF, right? And the delta HF is equal to negative 411 kilojoules per mole. So when we solve all of this, for all of this, we get delta H5 is equal to negative 788 kilojoules. Now this is highly exothermic lattice energy. And the total reaction is exothermic because of the energy released when the lattice forms. So this is the energy that is released when the lattice forms. I will post homework online. All right, it's all on this stuff. All right, And you do not have to do this. Oh, you have one problem that you have to do this, but it's all the energies are given to you, all right? All right, so you calculate the lattice energy, which is how much energy is released when all those particles come together. Okay, like Hess's law, it's just like Hess's law, adding up all of the reactions together. All right, yeah. I'm sorry, what? Well, that's because I don't think it's not that I can do it. Quarter, I thought it was 4.5.
No, I was wrong.
It's 4.25?
Yeah,
Oh, so I just took another 0.25% hit?
yeah. If you look at the email, the list, it's like, 3 something. It says 3% or some percentage for advanced degrees. So if you have a
I'm
master's.
assuming it's on top of that.
That's the one thing I wanna know.
So it could be twice the percent,
One evaluation.
Hi, what can I do for you?
Miss
I'll let
Fox
you
said
know.
that you had tests.
I have tests. What
Yeah.
test are you looking for?
It was,
Okay, I have
An
right here, I have a
electron
folder
test?
that says Miss Fox tests.
okay. It's like an electron test.
Okay, here's your
From like a
bubble
few
sheet,
weeks ago.
because she left me bubble sheets. And electron and spectra test, honors. Are you
Yeah.
honors?
Yeah.
Okay, there you go.
Thank you.
Have a seat. And are you allowed to use that sheet you're holding?
Yeah.
Okay. Okay. Oh, I guess I can, look at this here. Hang on. Look at this here. Whoop. Okay. All right, let me open up my door because I'm supposed to have a kid coming to take a test. Let's see. What's up? How you doing, Madison? How you doing?
It said the note they sent,
What?
the note they sent says 4.25 base salary and 3.25 advanced degree.
Oh, well, that's good, so they're, at least maybe they're valuing the advanced degree, that's kind of a lot, 3.25. So 4.25 plus
That's 7.5.
3.25 is 7.5, so 7.5.
In other words, that's an actual raise.
So, right, that is kind of, that's 4,800 to me, almost,
So
so that's,
I just wanna find out, that's the one question that I wanna hear them say is that combined? It should be.
it sounds like it should be combined, yes. Sounds like
And
it
then
should
you
be
get that
combined,
one-time bonus thing for
right.